Welcome to Beyond the Comfort Zone Talking Shit with King-KAMBUF. Today, we're on a pretty specific mission.
Yeah, this one's different.
We're cracking open a very particular document. It's an advanced mentorship digest, something prepared specifically for a master practitioner in architecture, engineering, and planning.
The one the source material refers to as KING-KAMBUF.
Exactly.
And, to be clear, this isn't just a grab bag of industry trends. The full title is, let me get it right, Architectural Insights with KING-KAMBUF by The Services of KING-KAMBUF PS, Architecture Daily Mentorship Digest, Sunday, November 30, 2025.
That's a mouthful.
It is, but the title tells you everything. This thing is designed to deliver what the authors call, and I love this phrase, fully new and never repeated doctoral-level insights.
So it's a shortcut, a fast track to the very edge of what's happening globally in AEC intelligence.
Right. It's focused on the problems and the engineering solutions that most conventional projects they don't even know exist yet.
So our goal here is to pull out and really analyze the most cutting-edge stuff on how our built environment is having to evolve. I mean, to meet these really extreme challenges, both environmental and social.
It's a world where architecture isn't passive anymore.
No more concrete and glass just sitting there.
Exactly. Buildings are becoming active systems. They're, dynamically regulating sound, climate, even internal vibrations, a whole new ballgame.
And the material we're looking at today, it follows that path, that complexity.
It does. We're going to start with 3 really cutting-edge design concepts. Ideas where structures are actively responding to what's going on around them.
Okay.
Then we're going to dive really deep into the technical side, the engineering physics, stuff that's often invisible but absolutely critical.
The hidden forces.
The hidden forces. And then we'll wrap up by looking at some crucial structural lessons that have been pulled from some pretty high-stakes real-world failures.
It sounds challenging.
Yeah, it's definitely a challenging investigation, but I think a deeply rewarding one. So shall we jump in?
Let's do it. Let's get into the industry pulse, this idea of buildings becoming genuinely responsive. The first frontier you mentioned deals with sound and structure.
Kinetic facade fins.
Right, kinetic facade fins. This concept, it's being tested in these really high-noise cities I see here. Rotterdam, Brisbane.
Yep. And it completely shifts what a facade is. It's not just an enclosure anymore. It becomes an active filter.
So how does that work? What's the mechanism?
Well, the core technology is all about integrating these things called micro-servo arrays.
Okay, what are those?
Think of them as incredibly precise, very small motors, and they're built right into the mullion system of the facade.
The metal grid that holds the glass?
Exactly. And these little motors, these arrays, they're constantly and instantly adjusting the geometry, the angle of the facade fins.
Based on what?
Based on the ambient sand pressure levels that are being detected right outside the building envelope. It's listening.
So wait. If a really loud garbage truck goes by, or there's a spike from a construction site nearby, the building doesn't just block the sound. It physically changes its own shape to manage the acoustic wave that's hitting it.
That's it, exactly. The architectural outcome is, well, it's profound. These structures are transforming into real-time urban sound moderators.
Wow.
They're designed to manage reflected sound, sure, but the really critical application that the brief points out is reducing interior echoes.
Oh, okay.
Especially reverberation inside long corridors that are just constantly bombarded by that outside urban noise. So they're dynamically tuning the building's internal quietness.
I mean, if these fins are constantly moving, these tiny micro adjustments, we could be talking thousands of cycles a day, right?
Easily. Year after year.
That feels like a catastrophic engineering challenge waiting to happen. The brief actually asks for a solution to metal fatigue. I mean, how on earth do you design a joint, a fin to mullion joint, that can survive that kind of perpetual motion?
That is, as they say, the $100 million question. It really is. A traditional joint that's, designed for a static load or maybe a little bit of thermal expansion.
It would just shear off.
It would fail. Catastrophically, probably within months, not years.
Right.
We're talking about cyclical stress loads that are repeating every few seconds during the loudest parts of the day.
So what's the answer? What are they looking at?
The solution has to be in advanced material science and geometry. You'd be looking at high-yield titanium alloys, maybe, or even specialized carbon fiber composites.
These that have nonlinear elasticity.
Exactly, materials with incredible fatigue resistance. But it's more than that. The joint itself can't just be a rigid pivot. it has to function like a microdamper in its own right.
To absorb its own movement.
Yes, to make sure that the vibrational energy that's being generated by the servo system, and also just from wind loads, doesn't transmit back into the main mullion.
Because if it did,
It would compromise the entire facade system over time. You'd get a systemic failure.
the cost and the complexity of the materials alone, just to keep a building listening to its surroundings, that really shows you how high stakes this frontier is.
It really does. It basically moves the facade out of the simple structural budget and puts it squarely into the complex systems maintenance budget for the life of the building.
Okay, so moving from that acoustic dynamism to climate adaptation, the brief talks about ultra-rapid hydration cement.
Right. These new blends developed in places like Chile, New Zealand.
And the point isn't just to build faster, right? It's more of a necessity.
It's a survival tool. Absolutely. I mean, think about a construction site in a tropical or a subtropical region. A big storm can come in and just halt operations for days, sometimes weeks.
And if you're in the middle of a huge concrete pour,
You're done. You risk a total loss of that pour, or even worse, the catastrophic formation of what are called cold joints.
right?
These rapid hydration blends are optimized for exactly those kinds of climate-volatile construction windows. They let crews finish critical form work and pouring cycles in a matter of hours, not days.
So the whole scheduling mindset shifts. It's not passive anymore. You're not just looking at the weather forecast and crossing your fingers.
Yeah.
It becomes actively climate adaptive. You see you have a short, dry window and you maximize it.
Precisely. But like you mentioned with the fins, that speed, it's a double-edged sword. The engineering challenge that the source material details is all about designing a pour sequence logic that uses that rapid set time, but also actively prevents the formation of those cold joints.
Can you explain what a cold joint is for anyone listening?
Sure. A cold joint happens when you pour fresh, wet concrete on top of or next to concrete that has already started to cure, to harden, and they don't properly fuse together.
So you get a seam.
You get a permanent seam. And that seam is almost always a point of weakness in what's supposed to be a monolithic structure. It's a built-in failure point.
And with these ultra-rapid blends, that margin for error must be razor thin.
Unbelievably thin. If the crew is even slightly delayed between mixing batches or moving the pump,
You're instantly creating failure points across the slab.
yes. So how do you mitigate that? Logistically, it's a nightmare. It requires meticulous planning. Often, it involves thermal mapping of the slab during the pour itself.
You're mapping the heat.
The heat of hydration. When concrete sets that fast, it generates a significant amount of internal heat. If you don't manage that heat, it can cause thermal cracking, which just makes the cold joint problem even worse.
So they're using sensors inside the rebar?
Real-time sensor networks within the concrete itself. They monitor temperature gradients and basically guide the crew on where to pour next. You're essentially choreographing this massive, very fast, temperature-sensitive operation.
That's incredible. Okay, and staying on this theme of water management, the sources bring up something called subtropical monsoon roof logic.
Yeah, this comes out of some really complex projects in Thailand and Vietnam.
And the idea here is that roofs are moving from being just static waterproofing surfaces
To dynamic rainfall choreographers.
Choreographers, I like that. How does that work?
It's a recognition that, a traditional flat or slightly sloped roof in a monsoon climate just gets completely overwhelmed. The sheer volume and the energy of that tropical rainfall is too much.
So what's the new logic?
The concept uses something called hydrophobic mesh weirs.
Okay, break that down.
Think of them as engineered nets or channels made of material that actively repels water, and they're placed strategically all across the roof surface.
And the function of these weirs is
They're designed to actively break down the monsoon sheet water.
sheet water,
Right.
like the single sheet of water flowing across the roof.
Exactly. Normally, all that water flows as one single overwhelming sheet. It creates enormous localized pressure on the roof membrane, especially at drains or where the water pools.
And that's where you get leaks and tears.
Always. But by using these weirs to fragment that one big sheet into thousands of smaller, manageable microchannels, you distribute the load. You prevent the membrane from getting overloaded and tearing.
That's a fundamental physical workaround. It's not about just making the membrane stronger. It's about reducing the kinetic energy that's hitting the surface in the first place. It's fluid dynamics applied to roofing.
That's exactly what it is. It moves the entire system into the realm of dynamic pressure management. It ensures that even during a peak storm, the whole drainage system from the roof all the way down to the internal collectors is operating within manageable flow rates.
Okay, the third big frontier mentioned here deals with buoyant urbanism and thermal memory. Let's start with these floating transit stations.
Right. Pilot projects in these incredibly dense rising river cities, Dhaka, Yangon.
And this is a direct climate response.
It has to be. As river levels fluctuate so dramatically, especially during monsoon seasons, any traditional fixed transit infrastructure just becomes unusable. It's either flooded or it's 10 feet in the air.
So these projects are using floating terrestrial aquatic transit hubs.
That's the term. They're basically anchored systems, and they feature these modular docking spines.
And the idea is that these spines can rise and fall with the monsoon levels, but they have to somehow maintain strict accessibility standards, right?
That is the absolute core of the challenge. The entire system has to maintain ADA flow.
So ramps and platforms can never be too steep.
They can never exceed a specific slope threshold. It doesn't matter if the river has dropped 5 meters or risen 3. The structural system has to be fluid. The transit becomes
Buoyant urbanism.
There you go.
The engineering problem defined in the brief, it's about defining a boarding platform geometry that stays level and accessible during these constant fluctuations. That suggests something really complex, probably computerized.
You're looking at things like integrated passive hydraulic systems or maybe massive helical anchor systems that are adjusting in real time. The docking spine itself is probably made of multiple shorter segments,
Each with its own brain.
each with its own independent sensors, constantly measuring the water level relative to the fixed riverbank. The whole goal is to articulate that spine so smoothly that the transition slope is basically imperceptible to the user.
So accessibility is guaranteed even while the whole structure is in continuous motion.
Navigating flood stages, yeah.
And then finally in this segment, we have thermal memory transit shells. The brief mentions electrified bus depots in places like Barcelona and Melbourne.
Right.
What are these shells made of, and how do they remember thermal loads?
They use these really advanced composite panels, and they often integrate something called phase change materials, or PCMs.
Of PCM.
They're materials designed to capture and release thermal energy very, very efficiently. So the function of the building shell is to actively store heat. Maybe it's solar gain from the sun, or it could even be residual heat from the bus operations.
And then it uses that stored energy for what?
To pre-warm the high-capacity electric vehicle batteries, especially during cold startup cycles.
Why is pre-warming the battery so important that you design an entire building around it?
Because battery performance is incredibly sensitive to temperature extremes.
Yeah.
This goes for charging speed, charging depth, and the overall lifespan of the battery.
So charging a cold battery is bad.
It's very inefficient. And it stresses the internal chemistry of the battery, which leads to degradation and much longer charging times.
So if these thermal memory shells can passively or semi-actively keep the batteries in their sweet spot, their optimal temperature range.
They dramatically reduce that charge time stress, they minimize energy waste, and they optimize the operational lifespan of what is, a multi-million-dollar electric fleet.
So the building stops being just a garage for buses.
Absolutely.
It's actively modifying the operational behavior of the electrical systems inside those vehicles. It becomes what's the term here? A thermal behavior moderator.
That is the essential takeaway. It's a piece of critical operational infrastructure. It's an investment that translates directly into massive energy savings and a longer service life for the vehicles. The depot becomes an active part of the city's overall energy grid management.
That dynamic view of architecture is a perfect lead-in to our next segment, mastering invisible forces. The source material here is pulled from these really high-level professional study blocks, the kind of engineering physics that really separates a highly resilient design from one that's just adequate.
This is where we get into the really subtle stuff. We're talking about modeling forces you often can't see or smell or hear.
The tricky stuff.
This is where we move into the realm of, subtlety, scalicity, hidden failure mechanisms. So let's start with dynamic structural and material risks. And the first one is the CLT question.
Cross-laminated timber.
Exactly. Why must cross-laminated timber schools evaluate diurnal moisture and inversion drift?
Okay, diurnal is the daily cycle. So we're talking about how the structure responds every single 24 hours. What is this daily moisture cycle actually doing to the wood panels?
Well, this whole phenomenon is driven by daily swings in temperature and humidity. The wood panels, they're hygroscopic, meaning they absorb moisture.
Like a sponge.
A very, very slow sponge. They absorb moisture overnight when it's cooler and more humid, and then they release it during the warmer day. This absorption and release causes these tiny but persistent alternating cycles of expansion and contraction.
And the critical insight is what that does to the structure.
The consequence is that this constant movement alters the lateral stiffness of the wall diaphragms at different hours of the day.
Wait, hold on. If the stiffness is changing, that means the entire building's resistance to lateral forces, like wind shear or a seismic load.
It's a moving target.
The building is literally structurally stiffer at 4 in the morning than it is at 4 in the afternoon. Is that what you're saying?
That is precisely the implication. And it's not just that the wood is swelling. It's about how the joints and the connections interact with that swelling.
Okay.
If the lateral stiffness of that wall diaphragm is significantly lower during a high humidity expansion phase, well, the whole structural model changes. An engineer can't just model the wall as a static element with a known stiffness anymore.
So what do they have to do?
They have to account for the CLT humidity gradients, the exact timing of the expansion, and the really complex interaction of that diaphragm with other parts of the structure that aren't moving. You have to treat the material itself as a variable stiffness element over time.
That makes the engineering calculation insanely complicated. You're modeling time as a structural factor.
You are. And it's not just a problem with timber. We see a parallel issue, though it's chemically different, in mixed material curtain walls. It's called silica phase moisture drift.
And the brief asks why engineers have to evaluate this. Given how many modern buildings use these refined silica-based composite panels for their cladding, this sounds like it could be a really widespread risk.
It is. It's like a microscopic but structural ticking clock. Moisture absorption causes these silica-based panels to go through these slight phase shifts.
What's a phase shift in this context?
Imagine the internal molecular structure just swelling or changing its density ever so slightly. This tiny alteration changes the material's inherent stiffness, and that changes the internal tension that's being applied to all the connections.
It's not visible corrosion.
No, it's a fundamental change in the material's property.
So the stiffness changes, which means the anchorage points holding those panels to the building are constantly under these fluctuating, unanticipated tension loads. That sounds like a fast track to connection failure.
It creates these highly concentrated anchorage risk zones. I mean, think about it. If the connection was designed based on the panel's stable, dry stiffness, let's call it 100% of its rated capacity.
Right.
But when the material gets wet, its stiffness drops to, say, 85%. Well, now the connection is overstressed relative to the material's actual capacity at that moment.
So designing for this requires a whole other level of analysis.
Advanced hygrothermal coupling analysis. You have to model moisture movement and heat transfer at the same time as you're modeling structural performance. It's incredibly complex.
Okay, let's pivot to human behavior as a structural load case. This one is fascinating. Analyzing torsion clustering during synchronized crowd movement in stadium concourses.
It's pretty humbling, isn't it? The idea that the joy or the excitement of a crowd can actually become a structural hazard.
It's wild.
It absolutely can. We're moving from physics into sociology and crowd dynamics here. This concept recognizes that large crowds, especially when they're reacting to a big event, a goal is scored, a crucial play, or even just a sudden rush for the exits, they tend to move in semi-synchronization.
And that creates a force.
A massive one. It produces these huge lateral torsion clusters across the structural concourse bands. It's a rotational, twisting force generated by collective human movement.
So it's not just the dead load of all those people standing there. It's the frequency and the size of their lateral swaying or jumping that really matters.
Exactly. The deep discussion points in the brief cover something called crowd resonance mapping. Engineers actually model typical fan movements and use that data to tune the deck plate frequencies of the concourse.
To make sure they don't match.
You have to ensure that the natural frequency of the concourse slab doesn't align with the likely frequency of human synchronized movement. If they do align, the slab will amplify that torsion. It'll resonate,
Leading to excessive vibration.
which can cause discomfort, panic, or even, over time, accelerated fatigue in the steel connections. You are literally designing the building to discourage collective structural movement.
That is a powerful example of treating human behavior as a critical structural load case.
So moving into extreme conditions and load anomalies, this next one is just incredible in its specificity. Why do airport terminals need jet wash lateral vacuum analysis?
Yeah, this one caught my eye. When I think of a jet engineer building, I think of blast force, air pushing away from the engine.
Right.
This is talking about a vacuum, a lateral pull.
It's a fantastic hidden force. So as a large jet, like a 747 or an A380, taxis past the apron side of the terminal, The sheer mass of air rushing past the fuselage combined with the engine turbines.
Creates suction.
A powerful aerodynamic suction gradient. And this vacuum literally tugs outward on the curtain wall panels. It's trying to pull the glass or the cladding right out of their frames.
How big is this force? Is it measurable in, pounds per square foot, or is it more like a huge instantaneous spike?
It's an intermittent, high-intensity spike. Standard wind load calculations are totally insufficient because they're designed to model large-scale distributed pressure.
And this is different.
Jet wash creates a highly localized, rapidly changing vacuum field. And depending on the jet size and how close it is, that outward pull can easily exceed typical design suction loads by 50, even 100% in a small area.
So what's the solution?
The discussion highlights the need for advanced computational fluid dynamics, CFD modeling, for this specific scenario. And that modeling leads to a requirement for highly stiffened anchorage systems.
Thicker steel, bigger bolts?
Thicker steel plates, larger anchor bolts, all to resist that intermittent high-intensity outward pull force.
Wow. Okay, next up, the very specialized world of research facilities. Why do heavy water labs need to check for isotopic density load anomalies?
So heavy water, which is often used in nuclear research, is water where the hydrogen atoms have been replaced with a heavier isotope, deuterium.
And that makes it denser.
Denser than normal water, yes.
Yeah.
And when you store this stuff in large containment tanks, that isotopic mixture shifts the fluid density significantly.
So the tank is heavier.
It's heavier than you'd calculate using standard water density, but that's not even the main problem. More importantly, the seismic modeling for the fluid movement inside the tank, what engineers call the sloshing mass, is fundamentally wrong if you base it on standard water density.
So it's not just the increased weight stressing the foundation, it's the fact that the denser fluid actually moves differently during an earthquake.
Precisely. It changes the forces exerted on the tank walls and the anchors. If you model that sloshing mass incorrectly, you miscalculate the frequency response of the tank during a tremor. Denser water changes the period and the amplitude of the fluid wave inside the tank.
So you need a whole different model.
You need specific density tuning analysis and much more refined seismic modeling to make sure the containment slab and the anchorage can handle the higher inertial forces and that altered dynamic mass distribution during an earthquake. It often means designing specialized damping systems just to manage that unique sloshing behavior.
Okay, and finally for this section, the paradox of heat. Why do we need to model apparatus bay thermal plume uplift in fire stations?
This is thermodynamics as a structural hazard. Fire trucks, especially right after they come back from a call, are radiating massive amounts of residual heat.
Sure.
When these trucks are parked inside the apparatus bay, that heat rises very quickly, and it creates a concentrated thermal plume.
And this rising heat creates pressure.
Significant positive pressure, uplift. And it pushes up on the large overhead doors and also on the smoke vents that are designed to exhaust fumes.
And that upward pressure can actually be strong enough to deform the tracks of those huge doors, or even, critically, compromise the seals and the integrity of the emergency smoke vents that you really need to work during a fire.
The modeling has to determine if that heat-induced uplift is sufficient to stress those structural elements. And the answer specified in the brief is that this requires plume-triggered ventilation systems.
So the ventilation isn't just for comfort or fumes.
It becomes a mechanism for mitigating the structural stress caused by rising thermal buoyancy. You have to open the vents quickly, not just to release smoke, but to release the physical pressure that's created by the heat itself.
Our last subsection here is about vibration conversion and mitigation. And the source material references some cutting-edge German and South Korean research on something called electroacoustic structural damping. This sounds like straight-up science fiction.
It really is the next generation of resilience. Traditional damping, it relies on friction or fluid viscosity to absorb energy. This new approach integrates electroacoustic resonators directly into the concrete slabs and beams.
And how does it work?
The mechanism is a moment of physical brilliance. These devices actively absorb structural vibration, say from an earthquake or from heavy traffic, by converting that mechanical energy into low-frequency sound waves.
And then what happens to the sound waves?
They're dissipated harmlessly into the earth.
So the building is acting like its own noise-canceling headphone. But for deep physical vibration, it's actively canceling out stress.
It becomes an active vibration converter. The system is constantly sensing, calculating, and then applying counter-frequency forces.
But the brief says there's a major engineering challenge.
There is. It lies in the physical connection. How do you propose a beam-to-resonator connection detail that maintains the necessary stiffness to effectively capture the vibration energy?
While also enabling the efficient transfer of that energy to the resonator for conversion.
That's a paradox.
It seems like one. If the connection is too stiff, it might just break from the conversion process. But if it's too flexible, the energy won't transfer efficiently. It's like trying to play guitar with a rubber neck.
You just hit on the core problem. In physics, it's called impedance matching.
Okay.
It's about ensuring that the vibration energy doesn't just bounce back at the junction point. The connection needs to have the exact frequency response that encourages the mechanical energy to flow into the resonator system rather than reflecting back into the main beam.
And that probably requires some very exotic materials at the connection point.
Most likely composite materials with tuned densities, yeah.
Yeah.
All to maximize that energy flow while minimizing localized stress concentrations.
And linking back to this whole idea of invisible forces, we have microrail vibration echo. This is a crucial analysis for parking structures near rail corridors.
Right, and this deals with resonance intensification inside confined spaces.
How so?
So rail-based vibrations, they travel through the ground and into the foundation of a parking structure. And because a parking structure is basically just a stack of large, repeated, flat, horizontal deck soffits.
The undersides of the slabs.
Right. Those vibrations reflect and bounce around between them. They get trapped. And this creates what the brief calls echo fields and frequency traps.
So the structure itself amplifies the vibration.
It significantly intensifies the slab resonance. It's a structural feedback loop, making the whole structure shake much harder than the initial vibration would suggest.
And that can't be good long term.
No, it accelerates structural fatigue, it increases ambient noise for the users, and it compromises the longevity of the whole structure.
So what are the solutions?
It involves integrating localized damping materials. Often it's high-density rubber or specialized polymers. And you place them strategically under the deck soffits or right next to the vertical columns, specifically designed to absorb those trapped frequencies instead of letting them multiply through reflection.
We've spent a lot of time on physics, but architecture's real complexity,
Yeah.
it really comes out when it intersects with politics, with culture, with high-level public administration. And we're now looking at the types of major RFP engagements that would truly define a master practice like KING-KAMBUF.
And the primary focus here is a project called the Pan-Andean Cultural Infrastructure and Mobility Resilience Hub. It's in the La Paz and El Alto region of Bolivia.
And this is an extraordinarily complex, multifunctional project.
Driven by a very deep social and geopolitical need.
The scope is just staggering. It's a hybrid hub that integrates rapid regional transit, which is crucial for linking La Paz and El Alto, alongside indigenous governance facilities, advanced high-altitude engineering test beds, climate adaptation measures, and public administration spaces, all in one single structure.
And this project matters so much because it forces a convergence of expertise across 4 major disciplines that are usually siloed. They usually don't talk to each other.
What are they?
You need structural engineering that can handle the harsh realities of high-altitude loading, where, reduced atmospheric pressure affects material performance and wind dynamics.
Okay, that's one.
You need urban planning to manage the regional mobility flow. You need architecture that can articulate a very complex cultural identity. And finally, you need public administration expertise to manage the multi-jurisdictional cooperation between 2 powerful and often competing political entities.
That last point seems crucial. The brief suggests positioning this hub as a vertical cultural and governance machine.
A landmark that reveals how this mountainous region is negotiating its own future, its climate, and its mobility challenges.
A vertical negotiation chamber.
And in cities like La Paz, verticality isn't just about density. It's about social geography, it's about status. The building itself is a declaration of political intent.
So what's the most challenging piece of this, according to the digest?
The governance challenge. Proposing a governance room configuration that can physically accommodate 2 very different decision-making processes.
Which are?
Traditional, hierarchical city-level administration, and the highly participatory, often circular or decentralized, indigenous decision processes.
Right. Traditional administration that often means tiered seating, a fixed podium, a clear hierarchy of who can see whom.
Exactly.
Indigenous governance, on the other hand, historically emphasizes shared space, circle formats, non-hierarchical visibility. If you design a room that favors one over the other, you're making a pretty clear political statement about power.
The architecture has to facilitate plural governance without compromising either function. And you can't just use movable partitions because that just implies it's a temporary truce. The geometry itself has to communicate equity.
So what might a solution look like?
Well, for instance, you might have a space that's built on two concentric circles, a slightly different elevation. The lower inner circle could accommodate the indigenous process,
Okay.
and the slightly elevated outer circle could provide the technical, observational, and administrative support infrastructure, but without physically dominating the central decision-making space.
It's all about sight lines.
It's all about sightlines, making sure that no single chair or location is perceived as the ultimate seat of power, unless the current process explicitly requires that temporary hierarchy.
That sensitivity leads perfectly into these conceptual design prompts that are in the brief. They're designed to push architectural boundaries toward cultural and experiential articulation, starting with the plural governance amphitheater.
Right. And this is an exercise in metaphorical design, as the brief specifies. The goal is to design an amphitheater where the spatial geometry shifts metaphorically.
Without any mechanical movement.
No moving parts. And it has to represent core negotiation concepts: visibility, hierarchy, consensus, and dissent. The structure itself has to tell the story of the political relationships in the room.
But how can static geometry convey something as volatile as dissent?
One way is through the strategic use of light and shadow, or maybe material finish. Consensus could be represented by, say, a smooth, polished central floor plan.
And dissent.
Dissent could be represented by staggered, angular seating, or maybe recessions on the periphery that allow participants to physically withdraw slightly or observe from an obscured angle, but without actually leaving the space. It's a quiet architectural acknowledgement of disagreement.
And the prompt requires including at least one acoustic or daylight device that specifically symbolizes the balance of power.
A physical symbol of power balance.
Maybe a central fixed beam of light that, because of the structure's asymmetrical geometry, illuminates different parties equally at different times of the day.
There you go.
Suggesting that power is temporal and shared, not fixed.
Exactly. Or an acoustic reflector positioned in such a way that it only enhances the voice of someone speaking from the center. It effectively creates a natural, non-electronic podium that's only activated when the group decides to physically occupy that point of consensus. It forces the participants to engage with the symbolic design.
The second conceptual challenge focuses entirely on sensory experience, the rain sound archive. So this is a cultural archive where the acoustic identity is intentionally linked to rainfall intensity. It's about transforming storms into a public sensory experience.
This really challenges the traditional idea of an archive as this sealed, climate-controlled vault, right?
Completely.
Here, the external climate is integrated as a feature. The goal is sensory programming, using a heavy downpour to activate the soundscape of the archive, but in a totally controlled way.
The constraints on this are incredibly tight. The acoustic modulation has to be entirely passive. No microphones, no speakers, just structure and material.
And the rainfall has to be perceivable, but explicitly non-disruptive to the sensitive archive material and the patrons inside.
That requires incredible precision in water choreography and material choice.
I mean, imagine a roof structure that incorporates these specialized, deep-channeled eaves, or maybe large-scale copper rain chains that are designed not just to drain water, but to become sound diffusion instruments.
So a big copper funnel could catch heavy drops and turn that intense impact sound into a gentle, low-frequency hum.
While lighter rain might be directed over textured stone surfaces that modulate the drip into a rhythmic pattern that's audible but soothing.
The structure is basically an instrument that's being played by the weather.
Exactly. Ensuring that the sound of the storm is transformed from just ambient noise into a curated cultural experience.
Okay, let's wrap up our discussion by analyzing these two detailed, high-stakes scenarios. They really illustrate the core lesson here, that environmental forces and pressure systems have to be treated as dynamic performance phenomena, not static elements.
These are complex, multivariable failures, and these case studies really show the tiny margin of error we're trying to eliminate.
So first up is the coastal civic building failure. The issue was salt air differential bracing fatigue.
And this building failed way, way earlier than expected, just 3 years into its operational life.
The data here paints a really clear picture. You have high salt saturation in the air, up to 38% airborne particulate.
Combined with a massive number of wind cycles, over 16,000 significant cycles per year hitting the windward frame.
So it was a chemical attack layered on top of a mechanical attack.
The consequences were very specific. Fatigue displacement of between 0.8 and 1.4 millimeters. These are tiny movements.
But repeated 16,000 times a year.
Exactly. And that led to visible corrosion starting precisely at the gusset plate edges, which are the most critical connection points,
And the diagnosis was a progressive loss of lateral stiffness.
which would eventually lead to bracing buckling and catastrophic facade racking. The whole thing would just give way.
So the key lesson pulled from this failure is the mindset shift. Marine air is not just a corrosive element, it is a dynamic structural force.
And corrosion has to be treated as a dynamic performance phenomena that accelerates material failure under stress cycling. They feed each other.
So what was the resilience workflow to solve this? It sounds complex.
It was complex, very costly, but absolutely necessary. It had 5 steps. Step 1 was meticulous mapping of the fatigue differential between the windward side, the attack side, and the leeward sheltered side of the frames.
Okay, map the problem.
Step 2 was replacing all the vulnerable carbon steel gussets with duplex stainless steel nodes, a huge material upgrade.
Why duplex stainless steel specifically?
Duplex stainless offers superior resistance to something called chloride pitting, which is the specific type of localized corrosion you get from saltwater exposure that always starts at stress points, like the edges of the gussets.
It's expensive, but worth it.
It's very expensive, but it offers a nonlinear increase in life cycle resistance compared to standard structural steel. So step 3 was installing sacrificial anodes near the bracing ends,
Right. These are blocks of a more electrochemically active metal like zinc or aluminum.
designed to corrode instead of the steel structure. They provide cathodic protection.
So you're intentionally introducing a new manageable maintenance item, replacing these anodes every few years to save the much more critical, much more expensive structural steel.
It's a classic cost-benefit trade-off in resilience engineering.
Absolutely. So step 4 was introducing crosswind dampers. These are specialized devices designed to actively reduce the amplitude and frequency of that lateral pulse from those 16,000 yearly wind cycles.
Fine.
Step 5 was recoating the entire refurbished structure with a hydrophobic anti-salinity polymer, a final physical barrier against the airborne salt. It was a totally holistic intervention. Material science, electrochemical protection, and dynamic load mitigation all working together.
Okay, our second scenario is the negative pressure diaphragm drift in a hospital ICU wing. This one is terrifying because the failure is induced entirely by the internal environmental control systems.
Yeah, this one is scary. So an ICU has to maintain a negative pressure environment relative to the hallway.
Contain airborne pathogen.
Right. But during the HVAC commissioning for this wing, a pressure asymmetry was created. The supply and return systems were imbalanced, and that led to this slight but constant pressure differential measured between Nica 0.03 and Nica 0.07 inches of water gauge. That sounds like an infinitesimally small force.
It is, but it was constant, and it was acting across a very wide surface area. And the consequence
Was a significant structural deviation, diaphragm drift, a physical distortion of the floor plate.
4 to 6 millimeters of deviation across a 12-meter span.
And this subtle structural distortion,
Yeah.
what did it cause?
It resulted in partition cracking, misalignment of crucial, sensitive medical equipment, and significant disruption to patient care. The failure mechanism was just air pressure, acting as this relentless, low-magnitude structural load.
The lesson there is crystal clear. Pressure systems exert structural influence. HVAC commissioning has to be treated like a structural load case, not just a systems test.
Absolutely. And the workflow to fix this was also really complex. 4 steps. First, pinpointing the negative pressure nodes that were driving the uneven loading.
Find the source.
Second, physically reinforcing the affected zones by adding supplemental drag struts to counteract that constant pulling force.
But how do you add structural reinforcement to a functioning ICU without compromising sterility or operations? That seems like a massive logistical problem.
It demands surgical precision. You have to use temporary negative pressure enclosures around the work zone. You're basically creating micro-clean rooms for construction inside a functioning ICU.
Wow. Well, what was step 3?
Installing pressure-controlled balancing dampers throughout the system to stabilize that air asymmetry. These dampers automatically adjust the airflow to maintain the precise pressure needed for pathogen containment, but without creating the structural drift.
And the final step.
Reconfiguring the supply return routing itself to eliminate the pressure nodes that caused the problem in the first place. So it was a solution that married structural reinforcement with a total mechanical system rebalancing. It just underscores how interdependent modern architectural systems are.
And finally, a quick code insight on NFPA 14. This is about standpipe remote hydraulics for tiered campuses.
Right, fire safety in complex geographies. This targets a really common oversight on these sprawling multi-level campuses that are built on hillsides or steppe terrains.
Because standard fire code kind of assumes a flat site.
It does. But campus geometry fundamentally complicates fire hydraulics. The standpipe pressure has to account for both the vertical separation, the height difference between floors, and the horizontal dispersion, the distance the water has to travel across the campus.
So you can't just calculate the necessary pump pressure based on the height of the tallest building or the distance to the furthest hose.
You can't. The ultimate insight here is that tiered campuses require independent remote hydraulic checks for each and every elevation cluster.
So if you have a group of buildings 50 feet higher than another group,
They function hydraulically as two separate systems. Each one needs its own pressure calculation. The brief notes that in these scenarios, the required remote hydraulic increments can often exceed the minimum design pressures by 10 to 25%.
just to make sure you have adequate flow and pressure at the highest, furthest points.
Exactly. The design has to adapt to the elevation logic of the site, not just the building height or distance.
So if we synthesize all of this, all these incredible insights from this digest,
From the kinetic sound fins adjusting their geometry in Rotterdam, to the thermal memory shells optimizing battery life in Melbourne,
to the nuanced physics of moisture drift and thermal plumes.
the core theme is just utterly clear. It is the complete shift toward active, dynamic, and responsive architecture.
Buildings they're increasingly functioning like conscious entities. They're constantly sensing, adjusting, and modulating their environment.
And the difference between a resilient, enduring structure and one that fails prematurely. It increasingly lies in the architect's and engineers' ability to model and mitigate these invisible pressures.
The microreal echo, the lateral jet wash vacuum, the pressure asymmetry in an ICU, these are the forces of true architectural mastery.
And true mastery, which is what this material is designed to convey to the master practitioner, requires seeing architecture not just as a physical structure. You have to see it as a system that is interacting continuously and dynamically with unpredictable environmental, social, and political forces. The structure has to adapt.
Or it will fail.
Or it will fail.
Which brings us to the final provocative thought that was extracted from this advanced mentorship digest. Something for you, the listener, to carry forward and apply to your own scope of work. The question posed for reflection is this.
Which environmental forces have I ignored that could evolve into structural, political, or cultural design intelligence?